Now that we've talked about some of the basic elements of mass timber, it's worth taking a look at how we could apply these to an overall design project. What I'm showing here is an overall schematic idea in both plan, section, and overall massing about how to have an outdoor learning center. This learning center is sunken back into a hill. You have an ability to walk in from the top end. The bottom end is meant to be an open classroom. It's open to the outside. How do we then learn to frame this thing if we use our basic design elements? What specifically do we need to do in order to evaluate whether something can span these distances, how many elements we have, basic design ideas of trying to apply a structural frame once we know the material. First step in all of it is to think through the grid. Each and every one of these is the same footprint. Each and every one of these has very different framing solutions. Are they right? Are they wrong? The thing is, it depends. What's either the performance goal structurally, or is there an aesthetic goal? Is there an environmental performance goal? If you look through all of these, the very top right section here has the two walls on the side that really projects a particular view. If you want to add more light, you could add more columns along the side, lets more light in, allows more view to the side. Maybe it's too redundant structurally, maybe it's perfect. What if you opened up the two sides and went with girders in 4 columns? Or switched it and put a wall at the very end and left the two sides open? Or in fact, added more columns to it and had these things be more square bays? But of course, we can help inform what those choices are if we get into a little bit more detail about how these are assembled. One way is thinking about the relationship between the structural typology that you use and the functional qualities of the space that happen. In the top over here, you see a small apartment building. In this apartment building, I know it's a small module. Maybe I'm using the red CLT walls to 1 define the module and 2 be the structure. So I can have grid lines 1 through 6, A, B, and C. And all that works fine for that particular function. But if I took something with the exact same overall width and same length, but instead had to fit an airplane in there, there's no way that I could have all these different grids because it would break up that space. So in that case, then I'm going to have to change the structure entirely. In this case, have columns on the 4 ends to be able to open up all of the side. What makes this important is when you start to think of these things as stacked. One solution up above, in this case the housing, may not be a good solution when it comes down to the ground, which is where the airplane is. So look at the accumulated loads, they come down, where do they go? So thinking through then, is there a relationship between an overall building structure? Is there something that is pervasive throughout the entire building structure that works for all the functions? Or do we try to make accommodations for one type of function and another through the structure and assembly? Ideally, it gets us to this idea that there's a module or a grid. When you start to establish a structural module, this module then can be used as other planning things. Planning not just for doors, windows, floors, foundations. Once you stay on module, everything else tends to find a good, consistent answer in terms of what its dimension is. Structurally, it also helps you as well, because you can start with this basic idea that there's load collectors, deck, purlins, girders. Those load collectors go to load grounders, in this case columns, foundations, and then are stabilized with load stabilizers, diaphragm, X-bracing. If you were to size and generally figure out this one module, you could take this one module and then stack it and then array it. So instead of thinking about the complexity of one big, huge building, you could break it down into its module components and eventually work backwards, and then figure out that if you have this one module, that in fact can be repeated until you have your whole building. Back to our schematic design here, there's 2 general strategies I want to show you. One is if we had the main load collector that's running on the front of the building and back, or the other one where we have our load collector girders that are running in the perpendicular direction. What can we tell just before we know any sizing about the good, bad, and kind of ugly consequences of this? If we only had 4 columns on the corners and ran a girder that went across the front, we know that we have a lot fewer members, but we know that in these few members that we have, we're going to have much higher stresses. It's spanning 64 feet. Because it's spanning that far, we know that deflection is going to be an issue, and we know that it's functionally really flexible, meaning lots of stuff can happen within this space. So maybe that's worth all the hassle of it. Or what if we broke it down and got really redundant with the number of columns? In this case, breaking it down into 1, 2, 3, 4 different spans having the girder run perpendicularly, adding columns in the middle, what we might find here is, of course, we have much shorter spans, but now we have more members. Each one of these things now has less stress than it had before, a lot less deflection, but with all these columns in here, we've made it much more functionally restrictive. For the sake of demonstration, I've called these framing option A and framing option B. Framing option A, I have girders on the front and back. The back wall here is the retaining wall. Front wall then is the girder. You can see there's 32 feet in between where the columns are in this direction. And then the purlins, in gray, span 28 feet. In order to complete the whole building then, we'd need 1, 2, 3, 4 of them as an exploded array. In the completed frame you can see down below here. If we then do framing option 1B, when we turn those girders 90 degrees, we see the girder now spans 28 feet in this direction, where it was 32 in framing 1A. The purlins then are only spanning 16 feet here, where they were spanning 28 before. We have 1, 2, 3, 4 bays instead of 2. And you can see the completed frame down below. When you're putting this together and trying to understand what your load collectors are, you can figure out whether you want these things to be planar or stacked. So the stacked composite assembly here is showing you a girder, and the girder might have the purlins that are setting atop of it. You can see in the section down below. Maybe there's some sleepers in the deck up above, so it's this layered assembly. Or you could have it be a more coplanar composite assembly in which the girder and the purlins are all flushed out on top. You have the deck that sits on top of that. Or you could get rid of the purlins altogether and do CLT slab. And again, so what else can we learn from this? In order to get our estimates in terms of the size and depth for it, in red I'm showing you the tributary area that we would need to have in order to determine the size of the purlin. That's the purlin's tributary area. Or tributary area for the girder, in red showing you what that tributary area is. You'll see how this is important later when we collect the loads. The other thing I'm showing you is framing options for 1A. You can see the number of actual pieces of material we have, the size of those. They're kind of larger, but there's not that many. Come down here to option 1B. Again, the tributary area for the purlin, tributary area for the girder. Number of pieces in the framing option. You can see that there's more, but they're much smaller. So this could be estimated in terms of cost and even construction, trying to figure out whether 1A or 1B is a better economic choice. With all these, when we're doing our estimate, we'd have to know what the total load is. In this thing, I've made a couple estimates here based on a location and building assembly and overall code guidance. In this, I'm showing that there's a live roof load. In this, there's snow, or in other words, it could be rain. It's showing you a pretty high estimate for what that would be per square foot. The roof dead load is based on the actual assembly materials. Wood is generally lighter than this, but I'm being conservative with a factor of safety in here. There's a floor live load that's based on its occupancy, so you have a classroom and an office. A floor dead load, again, which is based on the actual construction, in this case mass timber. You can see, again, it's real heavy, having a factor of safety. What's our total load? It's the live load plus the dead load times the tributary area. So, our live load, this estimate, times its tributary area gives us that, which is our total W for the roof. Same estimation for the floor gives us a total W for the floor. We need the total W because we're actually trying to figure out then how to size the maximum moment and maximum shear for the girder. We can start with the total load, and again, repeating what we had before, times its tributary area for the girder and the purlin. And what we find doing the estimate here, and you can see that even though I could have mapped these out and graphed these out, I'm using this shortcut. The Vmax shortcut, W divided by 2, W again being the total load, Mmax shortcut, WL divided by 8 for a uniformly distributed load. All of this is a very fast way of finding out that the maximum moment, you can see there. The purlin over here, running through the same exercise, we have its maximum total load, in this case 8,400. Going down, Vmax, Mmax, all of this then gives us what the maximum moment is going to be. So how big are they? First thing I always do is go through the rule of thumb. A rule of thumb for a glulam purlin is about L over 15. You can see on the top here. So you take the length times 12 inches per foot divided by 15 gives us an estimate of around 26 inches deep. So that's telling us about what the 26 inches is going to be. Now, in order to find the actual size of it, what we're trying to solve for is then the section modulus. Because we know what the maximum moment is, because we found that on the previous slide, allowable bending stress for a glulam is a published value, 1,550 pounds per square inch. Working those together, we find what the required section modulus is. You can either do your section modulus by doing B times D squared divided by 6. On the top diagram, you can see where is B, where is D. These are solid members, so that would work. Or I look up in the general properties of glulam, and I find out these sizes. What I found is a 10 by 28 is 1,300 inches cubed, which of course meets and exceeds what we needed for our section modulus. 10 by 28, 28 inches deep. Okay, pretty close to what we had for our 26. That should work. We check our deflection. What we find out using the deflection formula is that we'd actually have 1 inch of deflection. The allowable deflection, if we use the L over 240, is 1.4 inches. So in other words, 10 by 28 works. You can go through the exact same exercise over here with the purlin, solving them for what its section modulus needs to be. Looking in the catalog, we find that a 6 by 18 is going to meet and exceed that section modulus. Checking the deflection, we have 1.6 inches, allowable is 1.06, allowable is 1.4. That purlin is acceptable. So what do we find? We find that a girder's 28 inches deep, purlin's 18 inches deep, and that matches pretty closely with what we found for our estimates. When we switch this for option 1B, where it's running the opposite way, what we see is that our maximum moment is way lower than it was before for both the girder and the purlin. So going through the exact same method that we went to before, we find Vmax and Mmax. Our rule of thumb, L over 15. In option 1B, we're estimating it's going to be around 22.5 inches deep for the girder, L over 20 for the purlin. We find that's going to be about 10 inches deep, significantly less than what we had for 1A. Solving then for the section modulus, we can see that in this one, a 6 by 24 is going to comply. Checking the deflection, we find that the 6 by 24, in fact, is acceptable. For the purlin, running through the chart, we find a 4 by 12 is acceptable and exceeds the section modulus. Going through the deflection, we find that that's also acceptable. Once we have general estimates for the depth of that, we want to try to figure out, is the column going to be okay? How much weight's coming down into the column? So what you can see in the gray rectangle here is the amount of tributary area that's generally going to be distributed to the column. So the roof has that, which goes into this column. And then from this point on the back side, we have the tributary area of the floor, which also goes in, joins in with the load of the column from above, comes down as distributed through the retaining wall, and then eventually supported by the foundation below. On the opposite side, again, you have the roof tributary load from the girder, comes down into the column, the floor load comes down, you can see then that load is doubled, and then it's resisted by the foundation. What we learned from column design is that one is you want to look at the overall compression, size of it and compression to make sure you have enough area. Generally, this isn't the controlling factor of column design, and especially with something good in compression like mass timber. What we're looking for instead, so you can test this out by looking at the allowable compressive stress, FC, and divide that times the load divided by area. And you find that in fact we're quite fine in terms of what's allowable. Unbraced length then, you remember the KL factor for the effective length. Our effective length, because it is braced, in this case you can see that it is fixed down below because it goes into the foundation. You can say that it's pinned, so we have a fixed and pinned, which is 0.8 for the K factor. So therefore, we can go to the column chart and we find out that sure enough, what we had estimated for our size of the column works. We check its slenderness ratio to make sure that it's under 50 because it's wood, and again, it works just fine. Making choices about our connections then is another aesthetic choice. So either these can be the purlin to the girder is something that's hidden and exposed. Hidden here with exposed, how it rests on the retaining wall. If we chose to use CLT, how those would be doweled together, whether we choose to expose these with steel, whether we layer these or whether they're coplanar, and even how we start to use things like diagonals to brace it. Because of course this is one thing we haven't solved yet. Even if we have vertical members and horizontal members, we still need to figure out how to stabilize it. An unbraced thing is going to turn into parallelograms both in the X and Y direction. We could do it all with X bracing. You can see then X bracing on both levels, both in X and Y direction, front and back, end to end. You could then change that around and have X bracing on both the walls, two sides, or walls in the back. Knee bracing, where we're using a Y-shaped or moment-shaped connection to have that bracing. To do that, aesthetically, that's not really what we're after. So you could do X bracing and then walls. You could do all shear walls if you want, again in the X and Y, both on the front and two ends, or some sort of combination then between walls and bracing on the side. I'm going to pick the X bracing walls, floors, and roof because I've got a floor anyway. And if I have a floor anyway, then I know I can transfer those loads from one face to the other. And I also know that my roof can have some bracing as well, leaving those end walls open. What does that look like as one potential option when we're done? Well, we could have the CLT walls on the two sides that are providing the lateral bracing in that direction, open all the way through. In this case, you can see it's option 1B, where we have girders and purlins. Now, one thing to be concerned about is we don't see any bracing on the front side here. What we're counting on then, if we use the CLT, is that any load on this front face has to be transferred through and across both the floor and the roof in order to stabilize it. The roof right now doesn't have any lateral stability. So while this is a good option in terms of understanding the aesthetics, we know it's not quite done. There are other ways we can maximize this. Look at the potential for it. We know that a simply supported beam has a maximum moment in the middle, but if we started to do a cantilever out of it, we'd turn that into a negative moment and a positive moment, reducing the overall maximum moment. If we reduce the overall maximum moment, we reduce the size of the member itself. So what if we looked at framing options where we did cantilevers for both the roof and the floor? Doing that's going to allow us to thin this up even more. In this case then, with option what I'll call 2A, we have our columns, we have the girder that's out there, we stack the purlins on top and cantilever them out, do the same thing on the upper floor, and then the same thing with the roof. Because we're able to have those purlins on the first floor come out, it gives us a chance actually to move the stairway out from the two sides as well. So in that, you can see in the renderings down below that you have a stairway that's kind of centered, and instead of having two stairs, one on each end, you have one in the middle, and maybe improves its functional nature. What if we did cantilevers then with option 2B? In this, again, we have the same number of columns. In this case, the girder, we almost have to sandwich on both sides of the column. We can't have a cantilever that comes out this way and somehow magically goes through the column. We have to put one on both sides. In doing that, then, we can still run the purlins in between. We can still have a stairway that's run out front, stack it up above. The more detail you start to add to this, the more you start to understand the depth and the construction, you add a sense of realism to it, which really helps you to evaluate the quality of the design that you have. When you look at these particular options, so on the top you have 2A, on the bottom you have 2B. 2A on the top is where we have a girder on the front face in red, the purlins that are cantilevering out. You can see the value of that stair being moved to the front. We get our lateral bracing with the CLT wall panel in the middle. We get the bracing on the two ends with the X bracing, you can see there, and the bottom side there. But in doing so, we really define two big open ground floor spaces down below. We're able to define the classrooms on the two sides there, really open it up. For 2B, pretty similar strategy, except instead of having to brace it with a CLT in the middle, we're able to have thin bracing on the two ends there, opening up the whole middle space. In this case, you're putting that bracing there that defines the face of where that office space is on that side. And in fact, then the girders really lead you through the building. Breaks it up in terms of a planning module that's also a functional module, a view module. Is one right? Is one wrong? They're both right. Ultimately, this is the lesson. When you start to draw what those connections are, when you start to explore this thing with a certain level of detail, you're starting to reveal more about what your intentions are. You find that when you add the dimensions of the members in here, you model them together, you start to see how they work as an overall whole, then you can judge which one of these is what you think is your best option. One thing I'd ask you to do is to consider the diversity of tools that we went through even in this brief conversation. We started off with a general schematic massing, looked at some formulas, in fact, sizing, tried to figure out how many members there were to try to understand construction cost and complexity, did rule of thumb estimates, compared those then to formula estimates, drew it in 3D, amended it in 3D so we could add a cantilever to it, went back to the plan, moved around the stair, added other things to it, added all the connections, and eventually we find ourselves going through a relatively, what seems to be a complex process, but it's actually a relatively logical process of trying to either pick and test and make and break to see which one will maybe enhance our initial schematic idea.